So, in the last lecture we talked about test pattern generation, how we can generate tests. Now, one comment we made towards the end, we said that combinational ATPG is reasonably okay. We have tools that can generate combinational test vectors for even large circuits, but sequential ATPG is a problem. Firstly, it takes lot of time. Secondly, it does not provide good fault coverage, meaning it is often not able to detect tests for many of the faults, primarily because of the existence of the storage elements inside or the flip flops inside. It is not so easy to initialize the flip flops from outside. Okay. Now, unless you initialize the flip flop, so when you apply an input, you cannot say what the output will be, right. So, we have to go for some techniques called design for testability, because almost all the practical circuits are sequential in nature. So, we cannot use a sequential ATPG tool because they are very slow and not so good. So, we try to solve this problem in a different way. Let us see that. So, what is the basic motivation behind design for testability? DFT means they stand for a set of design techniques that makes test generation and test application easier and cost effective. This is a very general statement, okay? But how? Specifically, the DFT techniques that are used in practice, they address the difficulty of sequential circuit testing. You see, I mentioned that for sequential circuit, the main hurdle are the flip flops. They are sitting inside that black box which is the circuit, and I can apply inputs only from outside. So, unless I initialize the flip flops, I cannot run a test. This is a major problem of sequential circuit. So, for any design for testability technique, I have to address and find a solution to this question: how to initialize the flip flop rather easily, and how to observe the states of the flip flops whenever I want to. Normally, both these questions are difficult in a general sequential circuit, but now we are saying we would be framing some design rules, design for testability rules, which if we follow, it will make our circuits easily testable, right. So, the main issue was difficult to control and observe the internal flip flops. So, essentially the DFT techniques which are used, so one of them we will be discussing here, they try to make the internal flip flops easily controllable and observable. Controllable means we can initialize them to any value we want. Observable means we can see or read out their values whenever we want. So, if we can do this, then you see we have a very interesting, you can say, corollary to this. So, we are converting the sequential circuit test generation problem to a combinational circuit test generation problem. How? Let me just show you schematically. So, in a schematic sense, a sequential circuit looks like this. This is the combinational circuit part, these are the flip flops, you have the inputs coming, outputs going, and some outputs are coming to the flip flop, something like this. Now, what we are saying is that you see, these are my primary inputs, these are my primary outputs. Normally, in a classical sequential circuit testing, these are the only inputs and outputs I have. So, via this PI, we try to initialize the flip flops, that is why the problem becomes complex. But if we have a mechanism, let us assume we have, that we can initialize flip flops to any value you want easily, then you can say that, well, these inputs also can be easily set. We call them as pseudo primary inputs. Similarly, when we say we can observe the values of flip flops easily, here as if we are saying that we can observe these outputs of combinational circuit also, because it is these outputs that are going to the flip flop. These are called pseudo primary outputs. So, you see, once you have this, then I can forget my flip flop. So, I can treat this whole thing as a combinational circuit where Pi and Ppi are my inputs, Po and Ppo are my outputs, and I can use a combinational circuit test pattern generator to detect all faults here. So, I am not worrying about the flip flops anymore, but of course, how to test the flip flops, that we will have to address separately. Okay, fine. So, talking about the DFT techniques, broadly they can be classified as either ad hoc or structured techniques. Now, ad hoc techniques, as the name implies, they are really ad hoc. They are a collection of techniques, that means a long list of do's and don'ts. So, some designers, experienced designers, they have provided a list that you should not gate a clock, you should not do this, you should not do that. So, if you follow those rules, then your circuit will be a little better from the testing point of view. But structured techniques can totally solve the problem, as I have just now mentioned. There are now here we shall be looking at the scan path approach. There are variations to the scan path approach, partial scan, level sensitive scan designs, and several others. But if you look at the basic idea behind scan path, you will get the feeling that exactly what we are trying to do. So, this is the model of the sequential circuit that I showed just now, that you have a combination logic where the primary inputs and primary outputs are coming and going. You have the flip flops which are fed by a clock. Now, these outputs we refer to as the next state, and these inputs that are coming from the flip flop, they are referred to as the present state. So, you see, whenever a clock comes, the active age of the clock comes. So, whatever is here, that gets stored. So, the next state will become the present state, right. So, with every clock, this next state will come here, this will become the present state, and the next output that comes out from here, that will become the new next state. Okay. This process continues. Okay. Now, we come to the scan path design for testability technique. Now, as I had said, this is one of the most widely used technique. So, what do? We take a conventional sequential circuit just like this to start with. So, here there is no concept of scan path, we call it a non-scan sequential circuit. So, we can modify this circuit using an automated tool very easily to insert something called a scan path. This we will see what is a scan path. So, what are actually done, see here we are saying that we are modifying this circuit, actually we are not modifying the first part, we are modifying this part, the flip flop side. So, what we are actually doing is, we are replacing the flip flops, typically the D flip flops, they are replaced by a more complex version which is called a scan flip flop. So, a scan flip flop is essentially a D flip flop with a 2 to 1 multiplexer before it. So, a multiplexer followed by a D flip flop, that is a scan flip flop. Okay. So, we interconnect these scan flip flops in a suitable way, so that we can configure it as a shift register if we want. We add one extra additional input from outside, we call it as the test control input, and we add two more input and output lines called scan in and scan out as the input of the shift register and the output of the shift register. So, the idea is quite simple, that I have a test control from outside. So, if I set it to 1, then all my scan flip flops will be configured as a shift register. Now, once it is configured as a shift register, I can feed some data from outside from my scan in pin, and I can serially shift the data to all the flip flops. So, I can initialize them very easily. Similarly, if I apply clocks, the shift register data will be shifted out from the scan out pin. So, I can observe the states of the flip flop also. So, this is the basic idea, okay, how we are solving the controllability and observability problems. So, as I said, a scan flip flop is essentially a conventional flip flop with a 2 to 1 multiplexer before it. So, here I am showing a classical diagram using gates, but of course, in an actual VLSI chip this will be implemented using MOS transistors, but let us try to do a quick evaluation using gates. Okay. So, as you can see, in the normal D flip flop master slave type there are 10 gates, and for the multiplexer your logic overhead will be 4 additional gates, and this TC, which is the select input of this multiplexer, if I set it to 1, this will be my normal mode. The D input will be going to the input of this flip flop, multiplexer selects D. But if TC equal to 0 in this diagram, which is my test mode, where I have another input, I am calling it scan data or SD, this SD will come to this input of this flip flop. So, multiplexer selects SD. So, depending on the value of TC, either D or SD is selected. Okay. So, you can see that the flip flop requires 10 gates and this requires 14 gates. So, there is a overhead of 4 gates per scan flip flop. Okay. Now, this diagram shows how we have modified our circuit to configure them as a scan flip flop. Let us go back once more to this circuit. You see this circuit where the inputs are D, TC, SD, clock and Q. Q bar is normally not required, so only Q. So, if I can show this as a schematic, like here, let us say I show it as a black box. This is my so called scan flip flop. So, what are the inputs of my scan flip flop? I have a test control input, I have a D input, I have an SD input and I have a clock. In the output, let us say I have Q. This is my schematic of a scan flip flop, right. Now, using this schematic I will be explaining the next diagram. Fine. So, here I am showing an example where there were 3 flip flops. Normally, in the non-scan version, these flip flop outputs were directly coming to the input, like in that previous diagram I showed. Let me go back, this diagram. The output of the flip flops are coming as the input to this flip flop. This was the normal version of the flip flop. Now, I am making some changes here. Okay. So, what kind of changes? You see, the test control input is going to the TC input of all the scan flip flops. Okay. The combination circuit output is going into the D inputs, all of them, and scan flip flop output is going back to the input of the combination logic, okay, just like it was. But the additional thing we have done is that we have added a scan in input that is going into the SD input of the first flip flop, and the output of this one is going to the SD input of the second flip flop. This is going to the SD of this, and finally, this output is also going out as scan out. So, if I set TC equal to 0, then in the input multiplexer my this SD line will be selected. So, now my circuit will be a shift register, you see this path will be selected. So, by configuring it as shift register, I can shift in any data from scan in. So, I can initialize my flip flop or I can observe the states of the flip flop. So, this is exactly what we are trying to do in the scan based design. We are trying to as I said, we are trying to reduce the complexity of sequential test generation problem into a combinational test generation problem. Okay. So, some of the scan design rules have been formulated which a designer needs to follow. So, these rules you can easily correlate with the just previous diagram, this diagram that we had shown. The first one says that only clocked D flip flops should be used. So, you should not use JK or SR flip flops. Now, in fact, this is true for VLSI circuits, because in VLSI it is much easier to implement D type flip flops as compared to means other types of flip flop like SR or JK. So, this is an assumption which is followed almost universally today. Okay. And as I said, we need at least one additional primary input pin, the test control, and all the clocks must be directly fed. That means, it should not be a gated clock, like here you see, here although I have not shown the clocks, but the clocks are going directly into the 3 scan flip flops, okay, so that they can work in a shift register mode. So, clock signal must not feed any data input to the flip flop. This is one of the design rules. This is used to avoid race condition, because depending on clock skew and other problems, the data that is getting stored in the flip flop may be wrong. Okay. So, here I am showing an example. For example, suppose this circuit, as I said, that it now looks like a combination circuit. So, now the inputs will be Pi and present state, the outputs will be PO and next state. Suppose I use a combinational ATPG tool to generate my test vectors. So, these are my inputs, these are my outputs. So, let us say the ATPG tool has given me these test vectors. This I1 S1 is the input and O1 N1 is the expected output. So, I2 S2 is my second input, O2 N2 is my second expected output, and so on. But the problem here is that the way we have configured, like here this circuit, the Pi part we can feed directly. This is our present state, this is our next state. Okay. Now, whatever is my present state, I will have to load the flip flops with those values, that will come here, right. So, that cannot be done parallelly, that has to be shifted in serially in shift register mode. So, the present state has to be applied serially after setting, there should be T equal to 0, because in diagram TC 0 means the test mode. Similarly, next state has to be observed serially after setting TC equal to 0. So, this diagram shows in the axis of time what happens. From left to right, this is the axis of time. So, I am showing the inputs and outputs of the circuit on one side. Pi are my inputs, scan in is a single input, TC is a single input, PO are my outputs, scan out is another output. Now, you refer to this table. For the first test vector, I have to apply I1 S1, I am expecting this O1 N1 as the output, right. So, what I do, first I set test control to 0 and serially I shift in S1 through scan in. This S1 was my this part, present state part. So, I am serially shifting in S1 while setting TC to 0. Now, during this time Pi can be do not care, this solid blue region indicates do not care or random bits. But after I have shifted in, what is the status? Now, this S1 is already there in the flip flops. Now, I can apply, I can do two things together. Test control I set to 1, now it is a normal mode. I apply this I1 to the primary input directly. So, now I can observe the primary output of the combinational circuit delay. You see here, after I apply the inputs, so some of the outputs are going to the primary output and some of the outputs are going to the N1, but it is not yet stored in the flip flop. So, after the next clock comes, so it will get stored. So, what I do, I again set TC to 0, I apply clocks, and through the scan out the bits of N1 will come out. So, I am applying S1 serially, applying I1 parallelly, I am observing O1 parallelly, observing N1 serially. Now, one thing, while N1 is being shifted out, in parallel I can also shift in the present state of the next vector. Like here, while I am observing N1, I can parallelly shift in S2, because it is a single shift register, there is an output, there is also an input. So, via the input line scan in, I can start shifting the next one. So, in this way it can proceed. Okay. So, if you just look at a simple calculation, so means you can determine the so called scan sequence length. So, what is scan sequence length? It tells you how many total number of clock cycles are required, like here in terms of the time total how many clock cycles are required. Just only one thing you observe for the last let us say pattern. So, when you are observing the n for the last pattern, so for that the scan in there is nothing to shift in, this part will be empty. So, here I am showing it only a small snapshot. So, this already I have mentioned. So, the total scan sequence length, if you make a simple calculation, it will be ns plus 1 into number of test vectors. The ns plus 1, why? This is ns, this 1, 2, 3, 4, 5, 6, 7, this is ns, this 1 for here, and you repeat this for all the test vectors, and for the last one you need another ns to shift out the last n. So, this is my expression. So, where nc is the number of test vectors we have generated and ns is the number of flip flops. So, it is roughly proportional to the product of ns and nc. So, here I am showing a small example with actual numerical values. Let us say we have a circuit with 3 inputs, 2 outputs and 3 flip flops or state variables. Suppose a test generator has generated these 4 test patterns. So, I am showing a part of this diagram, this is called scan sequence. I am showing only a part of this scan sequence in the form of this table with the clock pulse. You see, for the first pattern the present state is 1 0 0. So, let us first shift this serially. So, for this we are setting TC to 0, we are shifting through scan in 1 0 0. During this time primary inputs I do not care, and PO and scan out we do not know, this can be anything. After this I set TC to 1 and I apply this corresponding PI 0 1 0, I apply 0 1 0. So, here when I apply 0 1 0, now the expected primary output 0 1 will appear after some delay. So, PO will get 0 1. But now to observe the other part, the next state which is 1 0 1, what I do? I again set TC to 0, apply clocks, so that over scan out I will get 1 0 1. Now, while I was doing this, I can shift in also the next present state 0 1 0. This also we are doing through scan in 0 1 0. So, these two things are getting overlapped. So, this will continue. I am only shown a small snapshot of the process. Now, talking about the scan testing time, well, we have only talked about how to apply the combinational test vectors, but what about the flip flops, the shift registers? Now, there is a standard way for testing shift registers. So, this says that you apply a shift sequence 0 0 1 1 0 0 1 1 like this. Let us take an example and illustrate what this means. Let us say I have 3 flip flops, they are configured as a shift register. So, in time I am just applying, let us say zeros, I am showing like this is my axis of time 0 0 1 1 0 0 1 like this pattern I am applying. So, in the output of the first flip flop, after 1 bit delay these bits will appear and this 1 will come out. Then again after 1 bit delay this bit will appear here 1 1 0 0, again the next one will go out. So, here again after 1 bit delay this will come, this 0 will come out. So, now you see, you look at each of the flip flops, look at all the flip flops. See, the flip flops are changing from 0 to 0, 0 to 1, 1 to 1 and also 1 to 0. So, I am exciting or testing the flip flop for all possible transitions. that is how we test a flip flop, that it can store each logic value and it can also have all possible transitions. So, just by applying this pattern serially, and if I observe that the same or the expected pattern is coming out here, so I can be sure that all these flip flops and also their interconnections, they are working correctly, right. This is how the shift register testing is done or carried out. So, the total number of clock cycles recorded or the number of bits recorded will be ns plus 4, ns is the number of flip flops and minimum 4 bits are required for this 0011. So, 0011 plus the number of flip flops, that many clocks are required. So, now the total scan test time or the scan sequence length will be not only this, plus this additional ns plus 4 will also get added. So, just a small example, if we have in a circuit 2000 flip flops and 500 test vectors. So, test length will be approximately the product of ns and nc, this is the dominant term. So, it will be about a million. Okay. So, testing will become slower, no doubt, and means another thing also you should remember that we are not testing the circuit at the rated clock frequency, we are shifting in the data in the flip flop, then you are applying the input and seeing the output. So, it is not that the circuit is supposed to work at 1 gigahertz, we are continuously applying inputs on 1 gigahertz and checking the output, not like that. So, we are not doing something called at speed testing, we are doing it in a slower rate. Okay. So, talking about the scan overheads, so as I said, at least one additional pin for the test control is necessary. Now, regarding the scan in and scan out, we can share them with the PI and P out pins, because if you have seen the diagram, you can see that we never use scan in and PI together, or we never use PO and scan out together. Only in the test mode I use scan in and scan out, we do not use PI and PO. So, we can share those pins for scan in and scan out, but at least one pin necessary for TC. Gate overhead will be, okay, this NG is the total number of gates in the combination logic, plus if NS is the number of flip flops. So, originally there were 10 gates in every flip flop. Now, after we added the multiplexer, there are 4 additional gates. So, 4 NS divided by this will be the percentage gate overhead. So, just a realistic figure, if your number of gates is about a lakh, 100k, number of flip flops is about 2000, 2k, then your overhead will come to about 6.7%. But of course, we have ignored the overheads due to interconnections and other things that will also need to be incorporated here. And regarding the performance, we have added a multiplexer in the combination path. So, that will be approximately 2 gate delays. So, the circuit will be slowed down. Similarly, in the flip flop earlier, the output of a flip flop was coming straight to the input of the combination circuit, but now the output of every scan flip flop will be coming not only to the input of the combination circuit, but also to the input of the next scan flip flop. So, the fan out becomes 2. So, increasing fan out means more delay. So, the clock will also get degraded. So, typically 5-6% degradation this occurs. So, in this lecture we have seen that we are using some additional hardware and also additional time, significant additional time to address the problem of testing sequential circuits. But you see, these additional time and performance degradation is acceptable, or you say must be accepted, because as otherwise it would be impossible to test the circuits of the type that we manufacture today. Okay. So, design for testability is a very important technique which is part and parcel of chip design today. Thank you.